Okay, so last time on Monday, I suppose, we started section 2.2 over different proof methods beyond what we learned in section 2.1. The first thing that we learned about was a proof by contradiction. That's where we're trying to prove a conditional statement like this one, if P then Q. And in order to prove this, we assume that P is true while Q is false, and show that it's impossible for that to happen by deriving some sort of contradiction. So that was our first method. Then after that, we talked about the proof by contrapositive. And this is related to the contrapositive that we learned about in the first chapter on logic. So if we're given a conditional statement, if P then Q, the contrapositive is logically equivalent to the original statement, and it's this proposition: if not Q, then not P. And sometimes it's easier to turn a conditional around in this direction with negations and prove it this way than it is to prove the original statement. And that's something that we saw in this example, where the original statement involves talking about a square and then the square root of this expression. And taking square roots can be challenging, and the way to get around that is to look at it in the reverse order. So instead of saying if x squared is irrational, then x is irrational, we say if x is rational, then x squared is rational. Okay. And then we had a brief proof over that as well. Just continuing on, reviewing a little bit, proof by cases. This is where the domain of discourse, the things that you're talking about, can naturally be divided up into cases like positive and negative, or maybe odd and even, or something similar. And then the last example that we did on Monday was this one, proofs of equivalence. And these are related to the biconditional propositions that we learned about back in chapter 1. So when we're talking about an equivalence in a theorem, we're talking about a statement like this: P if and only if Q. One thing that we discovered in chapter 1 is that this proposition, which is true when both P and Q have the same truth values, we discovered that this was logically equivalent to two conditional statements: if P then Q, so the arrow pointing to the right, and if Q then P, that would be the arrow pointing to the left. So for equivalence, proofs of equivalence, your proofs will naturally be broken into two pieces. You'll first prove this part, and then you'll prove the next part. And that's what we saw in our example last time about odd and even numbers. Before we do the final kind of proof from the section, does anyone have any questions over what we covered on Monday? Those first four kinds of proof. Okay, so all of the proofs so far that we've talked about, I believe, have to do with universal quantifiers. We're saying something happens for all numbers, or for all sets, or for all integers, something like that. Existence proofs are a little bit different. So these involve the existential quantifiers. And the most common way to prove a theorem of this form: there exists an x such that P of x, is by exhibiting an example. So just finding an example of a member of your domain of discourse, here I'm going to call my member A. So this is a value that we can plug in for x. Where P of A is actually true. So you're just coming up with one time where your proposition is true. So you need at least one time where whatever the proposition is that you're talking about is true. So here's an example. Let A and B be real numbers with A less than B. Prove that there exists a real number x satisfying A is less than x, which is also less than B. So we're saying that x is in between the two numbers. This is an existential proposition because we see the keywords there exists. So if we try to break this down into a symbolic form, it would actually look fairly complicated. This is one of the more complicated expressions that we've looked at because we're looking at any two real numbers. We're saying for all A and for all B, there exists another number x where this inequality works. So this would be the symbolic form. So it's actually something like 3 nested quantifier. And our domain of discourse here, we're talking about 3 numbers, 3 real numbers. So the domain would be something like, and I'm going to run out of room over there, something like R cross R, so that's ordered pairs, but we need 3. So we need another copy of R. This would be the domain of discourse. But even though this seems like a rather complicated expression, we still only have to do this sort of thing up here. So given 2 real numbers, we don't know what the numbers are. We just know that A is less than B. And really, we should have included that here. Something like if A is less than B, then. So it's even more complicated. But what we're looking for is just one number, x, that satisfies this. So let me write the word proof so that we can get started. In order to prove the statement, remember, we're letting the reader know what we're doing. We must find the number x. So we need to come up with the actual example. Where x is in between the two, A and B, whenever A is less than B. Okay, so this is how our proof gets started. Let's just come up with an example. So maybe A is equal to 1, B is equal to, what's a good number? 3. Can you think of any numbers in between 1 and 3? What's the first one that comes to mind? 1.1? Okay. Any other numbers? Maybe a little simpler? 2? Oh, 2.4? Yeah. So x equals 2 is the one I was hoping you guys would come up with. Because this one is exactly in the middle of the two. It's the midpoint. Between 1 and 3. Thinking back to maybe one of your algebra classes, can you think of how to find the midpoint in between any two numbers? So if I just give you two numbers A and B, what's the midpoint in between? Is there a formula? Right. So the midpoint in between them is the average of the two numbers. So let's pick that one. Because that'll work. And that's all you have to do on a problem like this. Good. Okay, so does that make sense? Are there any questions? Okay, so that actually wraps up this section, 2.2, over more proof methods. So I should point out before we go any further that your homework is already posted. Just make sure I show you where to find it, since we do have some extra time here. So if we go to Blackboard, find our course, your assignments for chapter 2 are in a new folder, so make sure you know where to find that here. Assignments, and then chapter 2. And then you can see your assignment for section 2.1 has already been posted, like I was talking about earlier. And then your assignment for section 2.2 is also posted with a due date of Monday. So that's 2 class days from today. And this homework has, I think, only 9 problems on it. Since these are proofs, they tend to take a little bit longer than other kinds of exercises. So make sure you guys are working on that. And let's see, I believe I need to post homework solutions for section 1.6 pretty soon.